Most of it is gone, cut apart with torches, melted down, sold off by the pound instead of by what it could do. 572 feet of machine, the longest land vehicle the United States Army ever built, torn to pieces before it did the one job it was built for. That is the fate this story ends at. Here is what does not add up. Nobody tore it apart because it failed. It rode on 54 wheels, every one turning under its own power, no drive shaft running the length of the machine, no gearbox, no single mechanical link that could snap and take the whole train down with it. Empty, it weighed 300 tons. Loaded, 450. Longer than the Titanic. Moved by 4 gas turbines feeding electricity straight into the wheel hubs because no transmission on Earth could have survived turning that much weight. 6 men lived inside its control car for days at a stretch, sleeping, eating, and navigating hundreds of miles from the nearest other human being. The Army shipped it to a proving ground in the Arizona desert, ran it through everything they could throw at it, and it worked. Every wheel pulled. The steering held through turns that should have torn the rear cars into ground the front had just cleared. The crew quarters functioned exactly as engineered. By any measure that mattered, the TC-497 Overland Train Mark II did precisely what LeTourneau built it to do. And within a few years, it was scrap metal anyway, cut apart, hauled off in pieces, most of 572 feet of proven, working machinery reduced to raw tonnage. Not because it broke, because something else quietly made the entire reason for its existence disappear. If you enjoy these documentaries, then subscribe. Thank you. Now back to the gritty history. The problem started with geography, and geography does not negotiate. By the early 1950s, the United States was building the Distant Early Warning Line, a chain of radar stations strung across the Arctic through northern Canada and Greenland, meant to give early warning of Soviet bombers coming over the pole. That was the entire strategic point of the network, enough advance notice to scramble interceptors and alert command before an attack arrived. But a radar station is only useful if it's staffed, fueled, and supplied, and building or resupplying one meant getting steel, diesel fuel, generator components, and prefabricated building sections to sites that had no port capable of handling heavy freight, no airstrip rated for large cargo aircraft, and absolutely no highway. There was no existing supply chain to plug into. Every pound of material had to be moved in from somewhere else, across ground that fought back the entire way. That ground didn't cooperate in any season. Winter froze it into something close to iron, then buried the iron under snow deep enough to swallow a loaded truck within its own length. Summer flipped the trap the other way. The surface thawed into standing water and bottomless mud sitting directly on top of permafrost that never actually thawed, so instead of solid ground drying out, you got a shallow swamp with a frozen floor a few feet down, the worst possible combination for anything riding on wheels or tracks. A wheeled truck didn't slow down in that mud. It went into the axles and stopped, engine still running, wheels spinning a hole straight down into the ground. A tracked vehicle chewed its own channel through the tundra and got stuck in it anyway, its treads packing mud into every joint and pin until the machine was dragging its own dead weight. Distances in that environment weren't measured in miles. They were measured in how many days a resupply convoy could survive before it ran out of fuel, snapped an axle in a rut nobody saw coming, or simply stopped moving and became one more wreck for the next convoy to route around. None of this was a minor logistics inconvenience the Army could simply absorb. The DEW line was one of the largest and most expensive construction and resupply undertakings the United States government had attempted since the Second World War, spanning thousands of miles across some of the least accessible ground on the continent, and its entire strategic value depended on stations that stayed staffed, powered, and operational through every season, not just the handful of weeks when weather happened to cooperate. A radar station that went dark because a generator failed and the replacement parts never arrived wasn't a maintenance footnote. It was a gap in the early warning line the whole system existed to provide. Every option the Army had already tried. Bigger trucks, more tracked vehicles, more fuel dumps staged along tentative routes kept running into the same wall. The ground itself was the obstacle, and no amount of horsepower bolted onto a conventional drivetrain changed the fact that a wheel without traction is just a wheel spinning uselessly in place. The man who believed he had an answer to that problem was R.G. LeTourneau, a self-taught engineer out of the earth-moving equipment business who had spent decades building machines other engineers assumed couldn't work, and then quietly proving that they did. LeTourneau's signature idea, the one that eventually made a 572-foot land train possible, was something he called the electric wheel, an oversized rubber tire mounted on a hub that contained its own electric motor. In a conventional vehicle, an engine turns a transmission, the transmission turns a drive shaft, and the drive shaft finally spins an axle and a wheel, with every one of those mechanical links capable of braking under enough load. LeTourneau's design skipped almost all of that. An engine somewhere on the machine turned a generator. The generator produced electricity. That electricity ran through cable directly to a motor sitting inside the wheel hub itself, with no gearbox and no drive shaft anywhere in between. Every wheel became its own independently driven unit, connected to the power source by nothing more than copper wire. That sounds like a modest engineering change. It wasn't. A conventional drivetrain has a hard practical ceiling on how big and how heavy a vehicle can get before the transmission itself becomes the failure point. Gears strip, drive shafts twist and snap, differentials overheat and seize under sustained heavy load. LeTourneau's electric wheel didn't have that same ceiling in the same place. Build a bigger generator, run more cable, bolt on more wheels, and in principle you could keep scaling the whole concept up almost indefinitely, limited by generating capacity rather than by the physical limits of spinning steel shafts. It was the kind of idea that looks obvious once somebody else has already proven it, and took a genuine leap of engineering imagination to arrive at first. In 1953, LeTourneau sold his earth-moving equipment division to the Westinghouse Air Brake Company. The deal came bundled with a non-compete agreement that kept him locked out of the conventional earth-moving market for several years afterward. For most inventors, a clause like that would have meant a quiet stretch on the sidelines, waiting out the clock. LeTourneau used it instead to push the electric wheel into territory nobody had tried applying it to before. Offshore oil drilling equipment built to survive out on open water, heavy logging machinery meant to haul timber out of ground no logging truck could get traction on, and Arctic transport, which happened to be exactly the problem the Army was wrestling with at the same moment. By the time his non-compete expired in 1957 and he returned to conventional earth-moving equipment, the electric wheel had already found its way into a growing line of Arctic overland trains. The Tourna train, the VC-12 Tourna train, the snow freighter, the side dump train, and the snow train. 6 machines built in total across the 1950s and into the early 1960s, each one testing the same core concept at a somewhat different scale, and for a somewhat different scale, and for a somewhat different job. The snow freighter is worth pausing on, because it shows how far the idea had already come before the Army ever asked for something bigger. Built for Alaska freight lines specifically to help resupply DEW line construction sites, it rode on 24 electric wheels, stood 14 feet tall, ran 16 feet wide, and could haul 500 tons of freight across ground that stopped conventional trucks cold. It worked well enough and reliably enough that it wasn't hard to imagine what the same basic architecture could do if it were built at several times the scale. That was the pitch, in effect. Not a new idea, but the same proven idea, pushed to a size nobody had attempted before. Each of those 6 machines, working through the 1950s, functioned as a working proof that the electric wheels scaled the way LeTourneau believed it would, and each one fed lessons directly into the next design. How much traction a given wheel diameter actually delivered on packed snow versus soft tundra. How the electrical system behaved under sustained cold weather load. What a crew actually needed to keep a machine like this running across days of continuous operation, rather than a single test run. By the time the Army came looking for a machine that could actually solve the DEW line resupply problem at full scale, rather than simply demonstrate that the concept worked in miniature, LeTourneau wasn't starting from a blank sheet of paper. He was starting from a decade of accumulated, field-tested experience, and the Army wanted to see exactly how far that accumulated experience, and the electric wheel concept underneath it, could actually be stretched. LeTourneau's answer to that question was the TC-497 Overland Train Mark II. Building a machine at that scale was itself a manufacturing undertaking most companies would never have attempted. The Longview plant had to fabricate, assemble, and test individual components. Axle housings, hub motor casings, structural frame sections for cars that would each carry tons of freight on their own, sized for a vehicle with no real precedent to design against. There was no supplier catalog for a 10-foot diameter drive wheel with an electric motor built into its hub, no off-the-shelf turbine mounting designed for a rolling power car, no standard reference for coupling systems that had to transmit steering coordination across 10 or more articulated joints without the whole chain developing slack or drift over 500 feet. Every one of those pieces had to be engineered specifically for this machine, then built to survive sustained operation in conditions far harsher than anything a factory floor could simulate. The fact that it came together at all, on a schedule that got it to Longview's yard finished and functional by February of 1962, says as much about the discipline of the build process as anything the finished machine did afterward at Yuma. The first thing to understand about the TC-497 is that its size was never a flourish. It was a requirement, forced by the math of the mission itself. A single DEW line resupply run wasn't a delivery of one crate or one pallet. It was tons of construction steel, fuel drums, generator components, and prefabricated building sections, all of it needed in a single push across terrain with no fallback plan if part of the load had to be left behind partway through. To carry that much weight without the machine's own structure eating up so much of its payload capacity that the trip stopped making economic sense, the vehicle had to be enormous. Big for the sake of the mission's actual freight requirements, not big for the sake of spectacle. So LeTourneau built big, using the same architecture that had already proven itself on 5 smaller machines. 54 wheels, each roughly 10 feet in diameter, each one an independent electric drive unit, with its own motor built directly into the hub, exactly like the Snow Freighter and its siblings, simply multiplied out to a far larger scale. No mechanical transmission ran the length of the machine, no drive shaft connected the front end to the back. Every one of those 54 wheels pulled under its own command, which meant the train's traction never depended on a handful of drive wheels dragging a long string of dead, freely rolling axles behind them, the way a conventional truck and trailer combination would. Every contact patch touching the ground was doing productive work, all the time, on every car in the consist. Powering 54 independent electric motors simultaneously took real generating capacity. And that requirement shaped the machine's second defining engineering choice. The TC-497 ran on 4 Solar 10MC gas turbine engines, each rated at roughly 1,170 horsepower, combining for a total output pushing close to 4,600 horsepower. One of those 4 turbines sat inside the control car itself, sharing space with the crew, the navigation equipment, and the living quarters. The other 3 lived in their own dedicated power cars, spaced further back along the consist, each one essentially a rolling engine room with no other job. None of those 4 turbines turned a wheel directly, and none of them were mechanically connected to the drivetrain at all. Each one spun a generator, the generators fed a shared electrical system running the length of the train, and that electricity was what actually reached the 54-wheel motors and put power to the ground. It's worth saying plainly here, because the story is about to raise the subject on its own terms. This was not a nuclear-powered vehicle. It ran on turbine-generated electricity from conventional jet fuel-burning engines, full stop, and nothing about the machine that rolled out of the Longview plant in February of 1962 involved a reactor of any kind. The Army would later study something considerably more ambitious for a hypothetical future version of this concept. That study never touched the TC-497 itself. The machine that was actually built, tested, and eventually scrapped used electricity purely as a transmission method, a way of getting turbine power to 54 separate wheels without a drive shaft, not as evidence of some exotic power source under the hood. That basic layout, turbines generating electricity, electricity driving wheels directly, no mechanical link between the two, is what let the finished machine reach the numbers it reached. Height at the control car ran over 30 feet, tall enough that the crew worked from something closer to a command bridge than a driving cab, with a clear vantage over the terrain ahead rather than a low, restricted windshield view. Behind the control car and the 3 power cars came 10 cargo cars, each one rated to carry roughly 15 tons, for a rated total payload across the whole consist of about 150 tons of freight in a single continuous train. On reasonable ground, all of that could move at up to about 20 miles an hour, slow measured against a highway truck, but 20 miles an hour of continuous, fully powered, all-wheel-driven progress across ground that would have stopped a conventional vehicle inside its first quarter mile, which was the only comparison that actually mattered. Solving the power and traction problem immediately created a second problem, and in some ways it was the harder one to solve. A vehicle 572 feet long cannot simply follow a steering wheel the way a car does, or even the way an ordinary tractor-trailer does. Turn the front car of a train that long through even a moderate curve, and basic geometry dictates that the cars further back will try to cut the corner, swinging toward the inside of the turn and colliding with precisely the obstacle, the rock, the ditch, the buried ice ridge, that the front of the train had just carefully steered around in the first place. On an ordinary truck and trailer, that's a manageable quirk any driver learns to account for. On a machine measured in hundreds of feet, it isn't a quirk. It's the difference between a train that can actually pick its way through broken, unmapped ground and one that methodically wrecks itself on its own rear half every single time the front end has to dodge something the crew couldn't see coming from 500 feet back. LeTourneau's answer was a coordinated all-wheel steering system engineered directly into the design from the start, not bolted on afterward. Every trailing car's wheels were steered in coordination with the lead control car, so that instead of cutting corners the way ordinary trailers do, each car further back in the consist reproduced the exact path the lead car had already taken, following through the identical narrow corridor of cleared terrain, rather than carving its own wider arc through ground nobody had tested yet. In effect, the entire 572 feet of machine threaded itself through one single tube of terrain, cut once by the front end and repeated car for car all the way to the back. It meant a crew navigating unfamiliar Arctic terrain only had to get the routing decision right once, at the front, and trust the rest of the machine to follow precisely rather than improvise its own way through. The system also had a documented reverse steering capability, letting the whole train back itself out of terrain it had already entered if a route turned out to be a dead end. That wasn't something the crew reached for casually. Backing a machine that long through unknown ground, even ground the train had technically already crossed once, forward, carried its own compounding risks, since the geometry that made forward steering coherent didn't simplify the problem in reverse, it just reversed the order of everything that could go wrong. Reverse steering was treated as a capability held in reserve for situations that actually justified the added risk and complexity, not a routine maneuver a crew would casually use to reposition the machine. There was a structural elegance underneath both of those solved problems, power and steering, that made them repeatable rather than one-off engineering tricks specific to a single fixed hull. The TC-497 wasn't built as a single rigid frame with dimensions locked in from the first drawing. It was built from interchangeable car units, power cars and cargo cars alike, coupled together in series, each one capable of being added to or removed from the consist as a self-contained module. That meant the overall length of the machine wasn't capped by some hard structural ceiling, the way it would be on a conventional vehicle built around one continuous chassis. Add more cargo cars, add the additional power cars needed to feed them electricity, and in principle the train could simply keep growing. 572 feet wasn't a maximum the design strained against. It was simply how long the Army chose to build the specific example it sent to Arizona for testing. None of that mattered if the 6 men actually operating the machine couldn't survive being that far from anywhere for the duration of a real mission. A DEW line resupply run wasn't a day trip with a return to base by nightfall. It meant days, potentially weeks, of continuous operation across terrain with no roads, no signage, and no fixed landmarks to steer by. Just featureless snow, ice, and tundra stretching out in every direction, indistinguishable from itself for miles at a stretch. So the control car wasn't simply a driving position bolted to the front of the train. It was engineered as a genuine mobile base, sleeping quarters for the crew to rotate through rest periods on a run that never really stopped, a galley for preparing food without needing to shut the machine down, toilet facilities, and radar and navigation equipment for finding and holding a route across ground that offered the crew nothing external to steer toward except their own instruments and careful dead reckoning. 6 men lived inside that 30-foot-tall front end for the full length of any run, which meant the control car had to simultaneously function as command post, navigation station, and living quarters, all of it stacked directly on top of an engine room housing one of the machine's 4 turbines, running continuously a few feet from where the crew slept and ate. Living inside that control car also meant living with the machine's maintenance burden, because a vehicle with 54 independent electric drive units and 4 separate turbine engines has 54 independent things that can develop a fault and 4 separate engines that can lose a component, all of it far beyond the reach of any parts depot. Every one of those wheels, at roughly 10 feet in diameter, was itself a substantial piece of engineering. A motor, a hub assembly, and a massive tire built to carry a share of 450 tons of loaded weight across broken ground, not a component anyone could swap out with a floor jack and a lug wrench. The whole design leaned hard on redundancy rather than on the assumption that nothing would ever go wrong. Losing a single-wheel motor out of 54, or even losing an entire power car's turbine, didn't have to stop the train, because the remaining wheels and remaining turbines could, in principle, carry the load and keep the consist moving toward wherever it needed to be. That built-in redundancy was as much a survival feature for the crew as the sleeping quarters and the galley were. A train that could keep moving even after equipment failures was a train whose 6-man crew wasn't stranded hundreds of miles from anywhere, waiting for a rescue party that, in the terrain this machine was built for, might not have been able to reach them either. Solve fuel hauling capacity and crew survival together, and you run straight into the problem that actually defines what this machine was, and more importantly, what it wasn't. On its own onboard fuel supply, the TC 400 miles had a range of about 400 miles. That's a serious number for a vehicle of this size and weight moving continuously across terrain with zero refueling infrastructure along the way. No depot, no fuel dump, nothing but what the train itself carried. But 400 miles fell short of the true distances involved in supplying installations scattered across the Arctic and Greenland, so the design allowed for extending that range by coupling in additional dedicated fuel and power cars, using the same modular system that let the train grow in length for cargo purposes in the first place. Here is the contradiction sitting inside that solution, and it's the kind of problem that only shows up once you've already solved everything upstream of it. Adding fuel cars to extend the train's range meant hauling additional fuel as freight, which meant a portion of the very cargo capacity the machine existed to deliver was now spent carrying diesel for its own turbines instead of steel and generator components for the DEW line stations waiting at the far end of the route. The entire point of building the TC-497 in the first place had been to escape the logistics burden that plagued conventional resupply convoys, trucks that had to carry their own fuel, refuel one another along the route, and plan their paths around fuel dumps rather than around what the mission actually required. Stretch the TC-497's range by coupling on extra fuel cars, and it started quietly recreating, in miniature, the exact problem it had been built from the ground up to solve. The machine could go farther, but every additional mile of range came directly out of its own cargo hold. That contradiction is precisely what pushed the Army to study something far more radical, a version of the Overland train concept that wouldn't need to carry its own fuel supply at all. Nuclear power in the form of a proposed compact reactor called the MM-1, targeted around 2,500 kilowatts, was studied as a way to give a future resupply vehicle something close to unlimited range, no fuel convoys trailing behind it, no fuel cars quietly eating into cargo space, no logistics chain stretching back to civilization across 1,000 miles of Arctic ground. A related, smaller prototype reactor called the ML-1, rated around 400 kilowatts, was actually built and tested by the Army. It never worked reliably. The MM-1 itself, the design that was actually intended for a vehicle at this scale, was never built at all. Nuclear power never reached an operational overland train in any form, on any test track, anywhere. It remained a paper study from start to finish, but a serious one, pursued far enough on the drawing board to reveal exactly how badly the Army wanted total self-sufficiency for this entire concept, and, by extension, exactly how far a purely turbine electric machine like the TC-497 still was from actually achieving it. Every mile of range beyond 400 came at a cost the design could manage well enough to function, but never fully make disappear. By the time all of that engineering had been worked out and welded into a single machine, 54 independently driven wheels, 4 turbines feeding one shared electrical system, coordinated steering that let 572 feet of hardware track through a single narrow corridor of terrain, a control car doubling as a full mobile base for 6 men, and a fuel range problem serious enough that the Army was studying nuclear reactors to get around it, the TC-497 was finally ready for its actual test. It shipped out from Longview to Yuma Proving Ground in Arizona in 1962, into open desert, onto ground selected specifically to push a vehicle exactly this way, loaded and unloaded, turning and reversing, running its systems under sustained operation rather than a quick demonstration lap. It worked. The coordinated steering held the train through its turns without the rear cars swinging wide into obstacles the front had already cleared, car after car tracking the identical line the control car had chosen. All 54 wheels pulled together as designed, delivering the kind of distributed traction the electric wheel concept had promised all the way back on the much smaller Arctic trains a decade earlier, just scaled up by an order of magnitude. The 4 turbines fed the shared electrical system without failure, running long enough and under enough load to demonstrate that the architecture held together at full scale, not just on paper. The living quarters, the galley, the navigation equipment, the whole mobile base concept, packed into the control car, all of it functioned as intended, supporting a crew of 6 through sustained test operations. This was not a vehicle that broke down partway through testing, or fell apart under its own extraordinary weight, or revealed some fatal flaw nobody had anticipated at the drawing board stage. Every hard problem the design had set out to solve, traction across difficult ground, steering an impossibly long machine without wrecking its own back half, keeping a crew alive, fed, and correctly oriented far from any base of support, got solved. In the field, under real load, in front of the people evaluating whether to build more of them. The testing wasn't a single pass down a straight stretch of desert road either. Yuma Proving Ground existed specifically to punish military hardware. Sand, washboard terrain, grades, and turns tight enough to expose exactly the kind of steering failure that would have crippled a 500-foot machine on its very first real corner. Running loaded and running empty, cycling the coordinated steering through the turns it had been designed to handle, cycling the 4 turbines under sustained load, rather than a brief demonstration burst. The TC-497 answered every question the Army's evaluators put in front of it. There was no moment where an axle failed under load, no moment where the rear cars swung wide and clipped an obstacle the front had cleared, no moment where the electrical system feeding 54-wheel motors from 4 separate turbines lost synchronization and left part of the train fighting the rest. Whatever skepticism existed going in, and building something this large on a wholly unproven scale invites plenty of it, the desert testing answered it directly, with performance, not with promises. By any engineering measure that actually mattered, the Overland Train Mark II was a success. It did the job it had been designed to do. It never once operated in the actual environment it had been built for. The Arctic-specific trials that were supposed to follow Yuma, sending the machine north onto the tundra and permafrost of the very DEW line resupply routes it had been engineered around from its first sketch, never happened. Not because the desert testing raised any doubts about the design, not because anyone in the Army stopped believing the machine could do the job. Something else had already made the entire argument for the machine's continued existence obsolete, and it had been happening the whole time the TC-497 was being engineered, built, shipped, and proven. Quietly, in a completely different corner of aviation development, with almost no overlap in personnel or program between the two efforts until the results collided. While LeTourneau's crews were still bolting together power cars in Longview, a different kind of machine was working through its own test program on the other side of the country. The Sikorsky CH-54 Tarhay, known in its civilian form as the S-64 Sky Crane, made its first flight in 1962, the same year the TC-497 was proving itself at Yuma. It was a heavy-lift helicopter, purpose-built to carry massive external loads slung beneath a stripped-down fuselage designed around exactly that job. And it exposed, in one stroke, the single assumption buried underneath every foot of the Overland train's 572 feet, underneath every one of its 54 wheels, underneath its entire coordinated steering system, its turbines, its fuel cars, and the reactor study the Army had commissioned to feed it. The assumption that a resupply vehicle had to physically cross the ground at all in order to deliver cargo across it. Everything the TC-497 was, every ton of it, every solved problem stacked on the last one, existed to answer a question the helicopter had just made irrelevant. Every engineering decision on the TC-497, without exception, was a solution to the problem of physically crossing terrain that actively resisted being crossed. The electric wheel itself, the coordinated steering, the reverse steering capability, the 4-turbine power plant, the fuel range extensions, even the mobile base control car built to sustain a crew across a journey measured in days rather than hours. All of it existed because wheeled and tracked vehicles could not reliably get through Arctic terrain, mud, snow, broken rock, rivers with no bridge, permafrost that swallowed anything heavy enough to matter. A heavy-lift helicopter doesn't solve that problem so much as step entirely outside of it. It doesn't care whether the ground below is solid, flooded, frozen solid, or open water with no crossing point at all, because it never touches that ground in the first place. Load the cargo at one end, fly directly over whatever terrain sits in between, no route finding through broken ground required, no steering system needed to keep 54 wheels tracking a single safe corridor, no risk of sinking to the axles in permafrost mud, and set the load down cleanly at the far end. Every problem the Overland train had been built, at enormous cost and years of accumulated engineering effort, to solve through sheer mechanical force on the ground. The helicopter simply flew over, treating the entire obstacle as though it didn't exist. That reveal didn't arrive as a single dramatic announcement inside the Army or anywhere else. It arrived as a gradual, then sudden shift in what made economic and military sense. Playing out across the same years, the TC-497 sat fully proven and completely idle after its Yuma trials wrapped up. Heavy-lift helicopter capability kept advancing steadily through the early and mid-1960s, and at the exact same time, the Vietnam War was pulling Army logistics budgets hard toward an entirely different theater. with an entirely different terrain profile, an entirely different set of resupply problems, and an entirely different sense of urgency. Money that might once have funded further Arctic-specific trials for the Overland train, an eventual production run, a fleet of the things stationed along the DEW line, went instead toward the logistics demands Vietnam was actually generating in real time. A 572-foot, 54-wheel, 4-turbine ground vehicle, engineered specifically for Arctic resupply, had no obvious role anywhere in that budget picture, especially once a helicopter could cover comparable missions without needing to solve the ground problem at all, and without needing to be 572 feet long, 30 tons of dead structural weight lighter, and immune to bad terrain by brute mechanical force rather than by simply flying above it. There was also a plain economic comparison sitting underneath all of it, and economics rarely lose an argument once a war is drawing down the budget available for anything else. A single overland train, built from a run of custom-fabricated components with no other customer and no other use, cost a fortune to design, tool up for, and produce, and every additional unit would have cost nearly as much as the first, since so little of it was standard hardware pulled off an existing production line. A heavy-lift helicopter, once developed, could be produced in numbers, maintained through an existing logistics and parts network the Army already had in place for its aviation fleet, and redeployed anywhere a mission required it, the Arctic 1 month, Southeast Asia the next, without needing to be re-engineered for each new theater. The overland train could only ever do one thing, in one kind of terrain, and it needed that terrain to hold still under it for hundreds of feet at a stretch. The helicopter needed nothing from the ground at all. Set against a wartime budget with more demands on it than money to meet them, that comparison didn't require much deliberation to resolve. The program ended there, quietly, without a formal verdict against the machine itself. The TC-497 never left Yuma Proving Ground for operational service. It never deployed. It never saw a single mile of the Arctic it had been designed around from the very beginning. It never resupplied one DEW line station, never crossed one stretch of permafrost, never once did in real conditions what it had already proven, conclusively, it was capable of doing in the Arizona desert. A machine that had passed every test put in front of it, that had demonstrated every one of its engineering solutions working exactly as intended under real load, simply had nowhere left to go. Not because it had failed at anything, but because the mission itself had been solved a faster, cheaper, structurally simpler way, while the machine was still being built to solve it the hard way, on the ground, wheel by wheel. What happens to a vehicle like that afterward isn't glamorous, and there's no reason it should be. The Army eventually sold the TC-497 off. There was no next mission lined up for it, no reserve fleet role waiting in the wings, no institutional plan at the time to preserve it as a historical artifact. Just a 572-foot machine sitting at a proving ground with no operational future and no obvious buyer for something built at that scale, for that one specific, no longer needed purpose. Most of the train was cut apart and scrapped where it sat. The power cars in particular, the units housing 3 of the 4 turbines, carrying the generators and the electrical infrastructure that had made the entire 54-wheel drive concept function as a single coordinated machine, were broken down for scrap value, the raw metal worth more sold off in pieces than the assembled unit was worth to anyone as a working vehicle with no mission left to run. The bulk of 572 feet of proven, fully functional engineering simply stopped existing as intact hardware. Torches went through hardened axle steel and cable bundles that had carried enough electricity to drive 54 separate motors, the same way a torch goes through a filing cabinet. No ceremony, no distinction made between the parts that mattered and the parts that didn't. Cutting torches accomplished, in a matter of weeks, what a decade of design work, 6 generations of prototypes, and a successful proving ground trial had spent years building toward. 54 wheel and axle assemblies, 4 turbine housings, 10 cargo car frames, and every foot of the cabling that had once carried electricity from 4 generators to 54 separate motors went to buyers interested in steel tonnage, not in what the assembly had once been capable of doing. Nobody involved in that process was being careless or wasteful in any petty sense. A piece of custom hardware with exactly one designed purpose and no possible second customer once that purpose evaporated has essentially one economic future once the program funding it ends, and it's the one the TC-497 got. That could easily have been the entire end of the story, a fully proven working machine quietly reduced to scrap metal because the mission that justified its existence had evaporated out from under it before it ever got to run. But hardware traced that specifically, built in numbers that small, rarely dead ends completely, and researchers who have spent years following what became of LeTourneau's Overland trains after they left service found something that outlasted the scrapyard. Some of the TC-497's running gear, wheel and axle hardware drawn from the 54-wheel drivetrain itself, has been connected to a one-off machine built later by an engineer named Lloyd Molby, a custom-built gold dredging rig nicknamed Gold Digger, put to work dredging placer gold out of the ground near Nome, Alaska. The connection isn't backed by a clean, unbroken paper trail with a bill of sale changing hands at every step. It's a link that specialist historians have traced through surviving hardware, photographs, and scattered documentation over years of dedicated research, and it's presented here with exactly that same honesty, a documented, traced connection, rather than an ironclad, provable chain of custody. But it is a real, sourced claim, not a rumor invented to give this story a tidier ending, and there is something almost darkly funny about where it points. Wheel hardware engineered to carry 450 tons of Cold War military cargo across Arctic tundra it never actually reached may have ended its working life turning gears on a gold dredge in Alaska, closer, in spirit and in geography, to the terrain it was originally built for than anything the TC-497 itself, as a complete machine, ever actually crossed in its entire operational life. Not everything went to the scrapyard or the gold dredge either. The control car, the actual front end of the train, the 30-foot-tall unit that held the crew, the controls, one of the 4 turbines, the sleeping quarters, the galley, and the navigation equipment, everything that made 6 men capable of running the machine and living inside it for days at a stretch, out of contact, far from anywhere, survived intact. It was preserved rather than cut apart for scrap, and it exists today, on display and viewable, at the Yuma Proving Ground Heritage Center, sitting in essentially the same stretch of Arizona desert where the whole machine once proved, conclusively and without qualification, that it could do exactly the job it had been engineered to do. That is what remains of it, not 572 feet of proven working machine moving 150 tons of freight across ground nothing else could cross, on 54 wheels that never once failed the tests put in front of them. One control car, 30 feet tall, standing alone in the same stretch of Arizona desert where it once towed 450 tons of its own weight across open ground under 4 turbines worth of generated power, the front end of a train whose other 500-plus feet no longer exist anywhere as an assembled machine. Most of that length was broken down for scrap value decades ago, reduced to raw tonnage, and sold off piece by piece. Some of it, if the historian's careful trace holds, is still turning today, far from any proving ground, inside a gold dredge outside Nome, doing a job nobody who designed it ever imagined, on the exact kind of unforgiving, half-frozen Alaskan ground the whole machine was originally built to cross. The control car sits in the desert. The rest of the train is somewhere else entirely, or nowhere at all.